How's it going, everyone? Today we're going to get started on our first set of actual calculus skills here on the Calculus Review. These are all derivative skills, so let's just see how they go. So we have a table of values here that gives two values of x, 3 and 4. And then we have values of two functions and those functions' derivatives at those values. So what's really going to happen here is we're going to take a look at the rules of differentiation and see how they apply in each of these situations. So I'll be writing the rules down over here in red, and then I'll evaluate that. So the derivative, start off with the rule, of a constant k multiplied by f of x is equal to k times the derivative of that same function. So if I want to do 3 times f of x, take the derivative of that, and evaluate that when x equals 3, well, that's just going to be equal to 3 multiplied by f of 3. So what is f of 3? It is, f prime of 3 is 1/4. So this is going to be 3 times 1/4, or just 3/4. So that's the first one. Long-winded way of saying it. I'm sure you had this way before I did. Here, the derivative of a difference is just a difference of the two derivatives. So this is just the derivative of f minus g is the derivative of f minus the derivative of g. Oh, what did I do? The derivative of g. There we go. So specifically, what we're going to get is the derivative of f minus g at x equals 3. That's going to be f prime of 3 minus g prime of 3. So what is f prime of 3? That's pi over 2. What is g prime of 3? That's -1. So I'm just going to leave it like this. You can do all the algebra to simplify that yourself. And you may want to ask yourself, is it even necessary to do that algebra? All right. Okay, so moving on to letter C, we've got the derivative of a product. So that means we're going to have to use the product rule. I'm sure you remember that. The derivative of f times g, that's equal to f times g prime plus g times f prime. And we're supposed to do this when x equals 4. So the derivative of f times g at x equals 4, well, that's going to be f prime of 4 multiplied by g of 4 plus g prime of 4 multiplied by f of 4. Classic problem. I have seen this on the AP test before. I'm sure you have, or you will be in your reviews. Very classic problem. What is f prime of 4? That is 1/4. What is g of 4? That is -3. Plus, what is g prime of 4? That's -2. Multiplied by, what is f of 4? That is 2. Again, go ahead and do the algebra that you need to simplify, if you need to simplify that, and then you're done. Quotient rule. Another very classic problem. Let's get the actual rule. F over g, the derivative of, is equal to, and the way I always remember it is low d high minus high d low, which Sounds like a sing-song to me. I don't know. So low is the function on the denominator. Low, d high, that means f prime, minus high, the function on top, d low, which would be the derivative of the thing on the denominator, multiplied by low, or g squared. And we're going to evaluate this when x equals 4. So let's do this again specifically if we're doing d dx of f on g at x equals 4. That's going to be equal to g of 4, f prime of 4, minus f of 4, g prime of 4, over g of 4 squared. Just like before, I'll let you do all of the algebra. I'll just put all the parts together. There's my fraction bar. So g of 4, that is negative 3. F prime of 4, that is 1/4. Minus, let's see, f of 4, that's 2. Multiplied by g prime of 4, that's negative 2. All over g of 4 squared. So that's negative 3 squared. Let's make sure we got this right. G times g is negative 3. F prime is 1/4. F of 4 is 2. G prime of 4 is negative 2. So that looks all correct. Simplify that and you got your answer. Moving on to letter E. So this is a combination of things. That's the rule from letter A combined with the sum of two functions. So the sum of two functions is f plus g, and that's equal to the derivative of f plus the derivative of g. So in our case, we've got the derivative of 5f plus pi g. That's going to be equal to 5 times f prime evaluated at, where are we evaluating this? 3. Plus pi times g prime evaluated at 3. So let's put all those numbers together. 5 multiplied by f prime of 3, which looks like pi over 2, plus pi multiplied by g prime of 2, g prime of 3. What is g prime of 3? G prime of 3 is negative 1. All right. Letter F. I'm going to have to cheat and go back up to get these values here. What is the derivative of the inverse of a function? Actually, I don't even know if this notation is meant to be for the inverse of a function. But if it's not, then letters F and letters G look exactly the same. So I'm going to pretend that this is meant to be the derivative of inverse of x. Okay, remember that's not to the negative 1 power. That's the inverse function of f. All right, we're going to need some extra space for this one. So let's scroll over to the side here and let's put it like this. If f of a is equal to b, that means that the derivative of the inverse at b is equal to 1 over the derivative at a. Okay, so that is the way that these work. So we're supposed to find the derivative at 3. So we're saying that we want at 3 the derivative. So that's got to be equal to 1 over f prime of some number where f of this number here, which we're leaving blank for now, is equal to 3. So the question we needed to ask before we continue is, when is the function f equal to 3? Well, the function f is never equal to 3, apparently. So I don't know that we can actually answer this one the way that I assumed that we were going to. Yeah, the f is never equal to 3 according to this chart. So perhaps maybe I'm wrong, and maybe they are asking for the derivative of f of x to the negative 1 power. Okay, well that's just the power rule. I think we got a handle of that. That's equal to negative 1 multiplied by f of x to the negative 2 power multiplied by f prime of x. So that's that chain rule. I think I have an extra pair of parentheses here, which we don't need. But that's the chain rule applied to the negative 1 power. So let's figure this out then. When x equals 3, we've got negative 1 f of 3 to the negative 2 power multiplied by f prime of 3. So let's put all of this stuff out here. Negative 1, of course. Negative 1. What is f of 3? F of 3 is 4. To the negative 2 power multiplied by f prime of 3. What is f prime of 3? That's pi halves. So there we have it. Negative f of 3 to the negative 2 power multiplied by f prime of 3. And the reason why I led us on that weird path was because letter G is the exact same question, isn't it? What is the derivative of 1 over G? Well, that's equal to what is the derivative of G of x to the negative 1 power, which, as we saw, that's negative 1 multiplied by G of x to the negative 2 power multiplied by G prime of x. And if we want to do this at x equals 4, this is just going to be negative of G of 4 to the negative 2 power multiplied by f. Why did I say f? G prime of 4. All right, let's plug in some numbers to this. There we go. So we have negative G of 4 is negative 3. That's going to be to the negative 2 power, multiplied by G prime of 4, which is negative 2. So go ahead and work that out. Lastly, if h of x equals f squared plus g squared, what is h prime of 4? Okay, so this is going to be a power rule. Remember that the derivative, I should have been doing this in green. The derivative of any function, let's call it f of x, to a constant power, we'll call that a, that's going to be equal to a multiplied by f of x to the a minus 1 power. That's just a regular power rule. But then we multiply by f prime of x. So you got to get that extra chain rule in there. Let's take a look at h. If h prime of x should be equal to, now that's f squared, so 2 times f, decrease a power, so f to the first power, and then multiplied by f prime of x, plus, again, let me scroll for you, g squared, the derivative is 2 times g of x to the first power, multiplied by g prime of x. And now we're evaluating this at 4. So h prime of 4 is equal to 2f of 4 multiplied by f prime of 4 plus 2g of 4 multiplied by g prime of 4. Let's get all those numbers in there. 2. What was f of 4? F of 4 was 2. Multiplied by f prime of 4, which is 1/4, plus 2 times g of 4, which was -3, multiplied by g prime of 4, which is -2. Work that out, and that is going to be your answer for letter H. Okay, so now we got a piecewise function on number 2. Piecewise function defining, what is this, f? And we're supposed to find the derivative. So the question is, what is the slope? Well, from x equals -3 to -2, I think there should be a negative here. From -3 to -2, this has a slope of 1. You can tell because it rise over run. So from -3 to -2, the slope is 1. Why did I put it at 2? The slope is 1. Positive 1. What happens at -3? Well, we can't really tell what the slope is at -3 because that's the end of the interval. And then at -2, that is at a corner, so the derivative doesn't exist at a corner. Now we're going to go from -2 to +1, and we got to ask, what is the slope of this line? And based on the fact that this is going down 2 units and over 1 unit, that sounds like the slope is -2. So do I draw a line connecting to -2? No, I don't. The slope is constant at -2. So we're going to draw a horizontal line at -2. This says a few things, most notably, or not, maybe not most notably, but just think about what happens when x equals 0. X equals 0 is right here. And if I wanted to find the derivative there, the derivative would be the slope of the tangent line at that point. Well, the slope of the tangent line is the same thing as the slope of that line segment, which is the slope of -2. So the derivative should evaluate to be -2. And then from 1 to 3, what is this slope? This doesn't look like, well, how far are we going up? We're going up 1, 2, 3, 4, up 5 units, and then going over 2 units. 5 over 2, that's our slope. So when we do this from 1 to x equals 1 to x equals 3, our slope should be 5/2, which is what, 2.5? So there's our slope. So we did part A, we sketched that graph, named the x coordinate for every point of discontinuity for f of x. Well, the derivative is not continuous at x equals -2. And it's not continuous when x equals 1. Now, at x equals -3 and x equals +3, the derivative is not defined, but it's not discontinuous either because it's at the end of the interval. So really the only places where we're discontinuous is at that -2 and that +1. And you could tell on this graph because here and here, those are corners. And as we know, corners of a graph are not continuous. Or, sorry, at the corner, it is not differentiable. All right, let's move on to question 3 here. What points do you suspect a discontinuity in the derivative? So is there any jumps or anything here? No. So this is none. How about over here? Well, here the derivative from the left is -1. The derivative from the right is +1 at x equals 0. That's also a place where there's a corner. So we have the derivative will not be continuous. The derivative is not continuous at x equals 0. Here, there is a horizontal tangent line at x equals 0. And that's another place where we have discontinuity. I mean, if the slope is undefined, if the slope is going straight up and down, that means the slope is infinite, doesn't exist. Letter D. 2/3. This is a cusp right here. So the derivative is not continuous at x equals 0. You'll notice that from the left side, the slope is negative, and then it goes to what looks like -infinity. And then from the right side, the slope is positive, and then it kind of goes to -infinity, but from the wrong place, or positive infinity, really. So yeah, not continuous over there. Similarly, right over here at x equals 1, that is a cusp, or it's a corner. I don't know what you want to call it, but this derivative is definitely not. The slope over here from the left side is positive. The slope from the right side is negative, and unless the slope equals 0 here at x equals 0, there's no way that it's going to be continuous. Last one we're going to do over here. Clearly, there's a problem when x equals 0. It just looks like a mess here. You can see it over here also. Eventually, so you're going to have to take the derivative of 6 over x. And the derivative of 6 over x is equal to, what is that, -6 over x squared. The derivative of 1 over x is always a handy one to memorize. So that derivative, since it will contain -6 over x squared, the derivative will not be continuous at x equals 0. So, finally, you may not have formally arrived at the suspect points above. Formal limit computations, as described in Appendix 2A, would rigorously prove derivative discontinuities. However, some of the examples used above would still seem difficult. In general, what characteristics on a curve would you believe the slope of the tangent line to the curve to be non-existent? So those are those rules: breaks, cusps, corners, vertical asymptotes. Let's see if I can spell this correctly. And finally, vertical tangent lines. Sound good? Okay, guys, that completes 3.1 to 3.3 concept review. This was all about derivatives, derivative rules, and when the derivative is not continuous. Make sure you go over it, and I will see you guys when we continue this tomorrow. Bye.